that you guys typically do this?
We typically like whiteboard stuff out. If you want to use the Zoom whiteboard, go for it, or just talk it out.
Okay, sounds good. So the first problem was
Wait,
rainbow.
don't start it. Okay, now you can go ahead.
Okay. So the first problem was rainbow bookshelves. And basically the premise of the problem is that Ellen has a lot of books that she's bought during summer, and they're of different colors. She wants to arrange them on her shelf based on the colors, where each shelf needs to have like a rainbow, which just means that like each shelf needs to have one book that's red, one book that's orange, and so on. Each shelf can hold up to 10 books, which means that like the 6 books have to be the rainbow colors, and then the 4 could be any color. So yeah, you read in like the input of like the number of books that she has, and then you also read in like lines of what color each book is. So that's basically the premise of it. The solution is just to loop through all the books that you have, and then for each book, just like keep track of each color and like how many books of each color you have. So I did this in just like an array, and then I just like added to that count each time I had a book of that color. And then I found whichever color had the minimum number of books. So say like red had like 3 books, and then like everything else had like 6 or more. So then the minimum would be 3. And so then you know that like you have 3 shelves that are going to be filled with rainbow books, because that's like the minimum rainbows you can make. So I just took so to find like the books that are left after you put everything on the shelf, I just found like the number of books. I subtracted from that like the min times 10, which is like the number of books that fit on these shelves, and then made sure that was like less than 0, or not less than 0, sorry. If it's less than 0, set it to 0, and then printed both the min and the books left. So that was the first problem. Does anyone have any questions? Okay, cool. Moving on to the second question. The second question was cute puppy vids. So that one, the premise is that Brant is using this app called TalkTick to watch a bunch of videos, and these videos can be up to 60 seconds long. He really likes puppies though, so he will only watch cute puppy videos. So if there's a video that has like something that's not a cute puppy in it, within the first 5 seconds, he'll scroll to the next video. And then the other cases are like if he's watched a combined 1 minute of non-puppy videos, then he'll get off TikTok or TalkTick, sorry. And then if he's been on TalkTick for 30 minutes, just combined time, then he'll get off. Or if he's out of videos to watch, then he'll get off the app. So you're given like n, which is the number of videos that are available. The next n lines contain the length of each video and whether or not they are a puppy video. So the solution to this problem was to iterate through like each of the n lines, and then kind of just keep going until like the total time that you have saved is greater than like the 30-minute mark, or the non-puppy time is greater than the 60-second mark. And then within this like loop, you can check like you can keep track of like the total length, and then the or like the total time that you've been on this app, the total, like check if the video is a puppy video or not. If it's not, then either add, if the video is like longer than 5 seconds, add 5 seconds onto your like non-puppy time, and to like your total time. And then if it's less, then you just add the normal time. And then you can add that also to your total time. And then if it's not a puppy video, then you can just add the length of the video. So then at the end, you just need to check that like your total time is like not greater than the total time that you're allowed to be on the app. If it is, then you return the total time that you can't be on the app. Otherwise, you return like whatever count that you've been iterating through. So that is cute puppy videos. Does anyone have any questions on that? Okay, cool. And the next question is bubble elephants, or no, it's not.
Sana's sun sketches.
Okay, we're gonna pass it off to Emily.
Yes. So for Sana's sun sketches, the goal is to
give a kind of a connect the dots page of a star polygon. So the polygon is defined by two concentric circles, one outer circle, one inner circle. So you're given the radius, the radii of these two circles and the number of rays or little spikes that need to be on the polygon. So first off, you know how many, that there's going to be 2n, n is the number of spikes on the sun. So there's 2n points that you need to make. So one way you can figure out the location of these points is by getting the angle that the point will be out from the radius, and then using trigonometry to compute the x and y location of that point. So what I did is I took 360 degrees divided up by the number of points, since they're all going to be evenly angled out as you go around. So 360 divided by n is the angle, and then write a function that takes the angle and the radius of the circle that this point's going to be on. So it'll alternate between being on the outside radius and the inner radius. So that'll change which radius you pass this function. And then you can get the x and y location by doing radius times cosine of the angle, radius times sine of the angle. With this problem, what's slightly annoying is that you have to go counterclockwise and you have to start from the top, like the topmost point, which is at 0, R2, which is the outer radius. So actually the math works out where you can just swap sine and cosine. So you make r sine be the x value and r cosine be the y value. And it will start at the top and go around clockwise.
Okay, cool.
For the decimal places, I saw someone asked about precision. In this problem, it specified in the output that it needs to be within a certain threshold of correctness. So it actually didn't matter. We had a custom checker so that even if no matter how many decimal places you output, it will still be okay. But yeah, it's good to notice on the output format, it'll tell you whether or not it needs to be like what precision.
Cool. Is that all the questions?
Cool.
Okay, cool. So
Moving on to bubble popping elephant. Yes, I'll go ahead and like whiteboard just to talk through the solution because I think it's easier to visualize a little. But for those of you who didn't read the problem, the idea is that you just have these like kind of set of intervals, one that's like positive, which I'll like do blue, and like one that's negative, which I'll do in red, which will kind of affect the size of this bubble that you're blowing. And you want to kind of output the maximum size that this bubble will reach. So like, I guess in this particular test case, things are a little big because things aren't to scale. But like, for example, it'll grow for 1 second. Let me switch colors. It'll grow for like 1 second here, and then grow and shrink, so it'll stay the same size, grow and shrink, so it'll stay the same size, and then grow again here, so it'll be like 2 here. Then it'll shrink to 1, stay the same size, and then grow again. So then the maximum size it reaches is 2, and the first time it reaches is like this time over here, basically. There are 2 ways to solve it, one that's nicer than the other in terms of implementation, but one that's faster. The easiest way, I think, is a time that is linear in terms of the total size or the max value of the intervals. So what you can do is, and I think I'll just switch to code for this. You can basically, instead of like analyzing these intervals as like separate entities, you just go through and process each interval like fully before you do anything else, which means you go through every spot that interval affects, and then you just add 1 or subtract 1 from that particular point. So to like show you what that actually looks like, I think it's this one. Yeah, so you just look through x and y is your like range of the interval, and then you just iterate through and then add 1 for everything in x to y, and then you subtract 1 for every negative interval. Then you just look through all those points and then kind of aggregate things as you go, and then print out the time with the greatest answer. So this is like relatively straightforward, but there's actually a cleaner solution that turns out to be a little bit more efficient. and can solve like different versions of this problem, such as when your A/B/C/D are limited by like say 10 to the 9 instead of 10 to the 6. And that would be by kind of processing the intervals themselves. So a nice way to do that is like this over here. You can come up with the key realization that you don't actually need to pay attention to every single time point. You only need to pay attention to the time points immediately before an event starts or immediately after an event ends. And like you have to do some paperwork, but you can convince yourself that these two times are kind of the optimal times, that the only times that you need to look at, because these will always be the times that are like optimal for you to end your bubble blowing. So I can go through like, I guess, a little bit more formal proof if anyone's interested. But once you have this idea, you kind of just create these events which represent the intervals in some sense, that represent the start and end of these intervals. So then for the positive interval, it'll be like +1 at the very beginning because that interval is increasing, and then -1 at the end because you want to cancel out that +1 change. And then the opposite for the negative intervals. You start at -1 and then cancel it out with +1. Then you just kind of like go through all these events and you keep track of kind of like what is the active change that you reach at this point, which is this variable active over here. And then at each point, you kind of like see the accumulated change that you have so far, and then just update the maximum bubble size just based on everything that you see. And this is a solution that's linear rhythmic, or like S log S, S log G plus S plus G log S plus G plus S, yeah. But this is definitely a nicer solution, although a little bit harder to implement. Does anyone have any particular questions? Okay, cool. We can move on to next problem then.
We had a quick question in the chat.
Oh, is there a fancy name for that solution? I think like the general kind of idea behind it is kind of like event processing is the idea. Like a lot of times when you have these like interval-based problems, they're often solved by considering what happens at the start and end points of all these intervals. Like for example, like interval scheduling, like that greedy solution is like another common example of like something where you only need to consider the start points and end points. In general, like you might want to look up things like event queues and that kind of thing. And there are probably a few examples from past UTPC contests if you're willing to like look through the previous links, but yeah, that's the general idea. Okay, cool. Next problem is, oh, Elon's Hyperloop, that's also me. Okay, cool. So this problem is was not written by me actually, and the previous problem wasn't either. I'm just explaining my solutions. But this problem is given kind of like n straight lines or like line segments of specified length. You want to create the largest closed polygon that you can. So like, I guess for the sample test case, let me erase my poor drawing. Okay, cool. Yeah. So for the sample test case, you have like a line that's like 20, which is like massive, and like 3 relatively smaller lines. So the idea is you can't use this 20 because this 20 is far too big. And if you use it, then you'll never be able to kind of close this polygon. But if you use the 3, 6, and 7, you can like build a 7 as a base and like 6 here and like 3 there. And this ends up being the valid polygon and ends up being the answer for this particular problem. The key idea here is like using the triangle inequality and figuring out how to extend it to like bigger shapes. So like triangle inequality is just like kind of indicates what the criteria is for like having a valid triangle. So if you have triangle lengths that are like A, B, and C, such that A is less than or equal to B, which is less than or equal to C. Sorry about my drawing writing. Yeah. Then you just, to have a valid triangle, you need to have A plus B is greater than or equal to, or strictly greater than, sorry, strictly greater than your biggest side length. And the reason this is just because like if you have A plus B equals your greatest side length, then you have your greatest side length, you have like A and you have like B, and then no matter what you do, this like A and B will always like match to this line exactly. You'll never get like a positive angle that makes this be an actual polygon. And this actually turns out to be the exact idea you need to solve this problem. So you can kind of extend this idea to like n polygons with n sides. So if you consider like the longest size in the polygon, you need to have that the sum of all the sides that are less size than that polygon have to be greater than the largest size. So like, for example, the sample case where it's like 3, 6, 7, and 20, 3 plus 6 plus 7 is 16, which is less than 20, which means that won't work. But 3 plus 6 is greater than 7, which means that that will work as a polygon. And like an easy way to see this, although like it's not the only way you can see this, is that what you can do is you can like take those like, so say that you have like a triangle that or say you're looking at like n line segments, right? And then you have your biggest one, and then you have like, I should use text instead. Say you have like n line segments, you take your biggest one and you have like n minus 1 line segments left. So what you can do is you can take those n minus 1 line segments, you can put n minus 2 and combine them into one like also super long line segment. And then you can take the 1, and then you can take like, so you can take the n minus 1 line segments and then divide them into 2 line segments, one that is like n minus 2 of the n minus 1 line segments, and one that is just the 1 line segment left over. And then you can form a triangle using those 3 line segments. And then if that triangle works, then you found a valid polygon. If you haven't, then it doesn't work for the same reason before, because if the sum of all those line segments equals the maximum side, then the best you can do is kind of create this straight line, which is an invalid polygon. So once you have this realization that you have to have all the lower side lengths exceed the sum of the highest side length, you can kind of just maintain a prefix sum and then find the largest point such that all the sum of all the previous elements exceeds the sum of the like final side length that you're choosing. And that ends up being the correct answer. Any questions?
It might be nice to just show them the implementation, just like.
Oh yeah. Okay, I'll go ahead and pull that up really quickly. Yeah, so this is like a fairly simple, just 10, 15 line solution. So you just take everything in, you sort all the line segments because you want to consider them from like least size to greatest size. And then you just see that if you have that your longest side length or the side length you're currently considering is less than the sum of all the side lengths you've seen so far, you set your new best to like the perimeter of that triangle, which is like all the side lengths you've seen so far plus the current side length. And then you end up just continuing to go and you print out the best answer at the end. Any questions?
I have a quick question.
Yeah.
Could you have sorted it in reverse order and then done a condition like if the cumulative sum kind of minus the current element is greater than that current element, then you have a valid one. And then you don't have to like store a best, you could just return it right there.
You could do that, yeah. But yeah, it's just like semantics and however you want to implement it at that point. I think that, I don't know, I don't think there's any big deal in like iterating through and like dealing with it as you come, because if you sort backwards, you still have to keep track of the cumulative sum from like the previous n elements anyways, which means you still have to like do that work anyways, so that doesn't save too much
But if
time.
you start from like the top, you could just start with the sum of all of the elements, right? And
yeah,
your
but then you
cumulative sum
still
is
have to calculate the sum of all of the elements,
Okay, sure. Yeah.
which means you just have to do that work anyways. Yeah.
Right, okay.
But yeah,
got it.
that's definitely a valid solution, of course. Yeah. Cool. Now we move on to, if there are no more questions, if there are, feel free to put them in chat. We move on to animal horizons.
Yeah, so I'm not sure how many people got around to reading it. So the problem goes like this, where you have this infinite grid, like these animals are in this world, like this infinite world, and you start at some point, x1, y1, and you're trying to get to some other point on the map. But you're told that certain points have an obstacle, a tree on them, and you want to minimize the number of obstacles that you run into on your way to the destination. So the idea behind these obstacles are that they all fit this mathematical pattern of like either the sum of the coordinates are divisible by some number passed into you, or the difference between the elements is divisible by a different number. And so we can, so like intuitively, you can see that this makes like diagonal gradients along like if you imagine like a grid, the grid of the space that you're in, it makes diagonal gradients of bad squares that you can't reach. But diagonals are hard to deal with because it's like, it's just not structured on, or it's harder to structure where you're going to run into that, like where you're going to be forced to cross that diagonal. So we can do something nice where, let me just show what I mean. So we can do something nicer where we can translate every point that's x, y, and we can make it into the coordinate x plus y, x minus y. And we know that this is like, we're guaranteed that this is a one-to-one mapping. Like we're never going to run into an issue where 2 points could be mapped to the same thing. And so this means that like the grid is preserved, as in like you have a unique start location and a unique end point, and you will go through a unique set of points on the way. But what this does now is, you know that if x plus y is divisible by the number, then that makes a vertical line of all these points that are bad. And then if x minus y satisfies the condition, that makes a horizontal point. So essentially you're left with some sort of grid structure where like you have a bunch of lines going this way and lines going this way along the graph. And what you're trying to do is figure out how big this grid in the middle is, and then how many of these lines will you have to cross to get from your source to your destination. And you can do this by just converting. So this converts the start location into this new coordinate system, and then this converts the end location. And then all I do is calculate what grid that each of the start x and the start or end x's, and then same for the y's. And then the number of grids that I have to go through is just equivalent to the maximum number of in each direction it is, because I can minimize it by going through. There will be points that satisfy both the x plus y condition and the x minus y condition. And so I can minimize the number of bad squares and jump to multiple sectors by going through those diagonal points, essentially. Let me know if you have any questions, but that's the general idea.
There's a question in the chat. I can read it. Was there a specific reason for making the problem involve mod 2m mod 2n rather than mod m mod n?
Yeah, so making it mod 2m will guarantee you that essentially it just makes the grid sizes a lot nicer. Basically, if you have an odd grid size, it's harder to guarantee that you're able to like satisfy what I think the math still works out the same, but I found that when setting up the problem, I found that doing an even grid size is a lot easier. And rather than guarantee that my input is even, just telling you to double it is a lot nicer.
We have another
just
question.
Semantics though.
Oh. Another question, why do you do the plus x1 is greater than 0?
This is just to deal with an off by 1 error, because x and y could be negative. So I'm not taking the absolute value when I'm doing this change. So if like, this is just my implementation. There are implementations that don't need this if you put absolute values in while you're working through, but I was lazy and this is just a cheap hack to do it. Yeah, it fixes an off by 1 error I was having. Any other questions? All right, cool.
Moving on to the final problem, which is Tree Wizard. I was particularly proud of the flavor text on this one. It involves our previous problem writer, Abulash. I highly recommend giving it a read if you haven't. But the general gist of the problem is you have this tree that's labeled with the numbers 1 through n, and you want to you have this like function on a tree, which will be like take the maximum label of that tree and the minimum label of the tree and subtract them. And then you basically want to look at like all valid like subgraphs of this tree, all connected subgraphs, which means like any like partial tree that you can create. And you want to apply this function to like all of these subgraphs and take the sum of everything. So just to give you a better idea of what that means, I wrote it on the sample case, but like it might be nice to just like do a picture. So like say we have some tree that is like this. I forget what the actual sample was, so I'll just do this, and I might be slightly different, but like it is approximately the same. So you have this tree, yeah, with like 1, 2, and 3. So this is a tree of size 3. And you want to consider like all connected subgraphs. What that happens to be are 1 by itself, 2 by itself, 3 by itself. So that's 3 of them. And then there's also 1 and 2 combined, 2 and 3 combined, and then the entire tree itself. Do people see why that is like all of the subgraphs? In particular, like for example, you can't take 1 and 3 without taking 2 because 1 and 3 aren't connected, so it wouldn't be a valid connected subgraph. So like you have all these subgraphs. In this particular case, all the individuals don't contribute anything to the sum because like 1 minus 1 is 0, 2 minus 2 is 0, 3 minus 3 is 0. And then each of the graphs that are of size 2, you have like 2 minus 1 is 1, and 3 minus 2 is 1. And then in the entire graph, you have 3 minus 1 is 1. So the overall answer for this like sample case is 1 plus 1 plus 2, or 4 overall, which is, I think, what you see in the sample anyways. So now we have to think about how we solve this in general case. In this example, we just kind of enumerated through all the trees, which makes sense here because n is only 3. But when n is 10 to the 5, and you start calculating these things out, you find out that there's actually an exponential amount of subtrees. So you don't have the time to enumerate through all of them. So you have to come up with some sort of clever counting argument to include all the subtrees you want to include. And the way to do that, or at least the way I did that, is through DP. First, the key realization is that, or one of the key realizations is that for this function where we take like, let's go back to text because writing is hard, where we take like max label minus min label. So this function is linear, which means we can like decompose it into the sum of the parts. So like, I really shouldn't have written it like this. So like sum of like max L minus min L equals sum of the maxes minus sum of the mins, right? Does everyone see why this is true? We're just kind of like separating this out. So rather than actually like finding all these subtrees and calculating this function on every single possible like subgraph, we can instead just figure out how to do it for the maximums or figure out how to do it for the minimums and then subtract the value of the first one from the second one. So I'll go through how to do it for maximums, and it's pretty symmetric to just do the same exact thing for minimums. The idea here is that you have that DPI, you have that, go back to text. You have that DPI is what you want to calculate, and it's the number of subgraphs / trees that have a maximum label of I, right? And if we're able to calculate this quantity, it's easy to calculate the sum of the max of all the labels, right? Because then it just becomes a sum of I times dpi for all I from 1 to n. Because all we need to do, because if dpi is the number of subgraphs of trees that have a maximum label of I, that means that there are dpi of these trees, and then that tree has a maximum of I, so then you just multiply by I to calculate all of this. And because every one of these, this includes all trees by definition, because, or all valid connected trees, are able to calculate this accurately, it'll just solve the problem for you. The way you can actually calculate this accurately is that you can consider processing these numbers in terms, oh, I see a question. I'll go ahead and answer it as we go. So the point is you're not supposed to find all the subgraphs. You're using a clever counting argument, which I've kind of outlined here. I haven't explained how to calculate this, to approximate finding all the subgraphs, but in a way that's a lot more efficient. Like there is an exponential amount of subgraphs, so you won't be able to actually find all of them, but you can calculate this dpi in linear time, it turns out. Or you can calculate all values of dpi in linear time, which means that you can find this value across all the subgraphs very cheaply, even if you aren't actually calculating the subgraphs themselves. So what you do is you actually process I from 1 through n, and like the base case is easy, right? So like for like dp1, this is just 1, because if you include any other node with that has a label, that label is guaranteed to be higher than 1, because 1 is a minimum label in the entire graph. So the only kind of tree that has 1 as a maximum is like the singleton tree with just 1 as a node itself. So like dp1 is easy. And the difficulty comes when we start reaching kind of like future states where the maximum can kind of interact with other trees. It turns out the nicest way to count things is that you can realize that dpi equals product of dpj for all j that are adjacent to I and j less than I. So, oh, sorry, dpj plus 1. So I'll explain how you get this. It seems kind of convoluted right now. But the idea here is you have like some tree that you start out with. Like you have like, going back to text, sorry. Yeah, you have like your tree with label 1 over here. And then you start processing the tree with label 2. And say that 2 is adjacent to 1, so this condition will apply. That means that because 2 is kind of like the maximum label that you process up to this point, you know that every label that you process before this is less than that, which means that you can include any label that you processed before this inside your tree that is at size 2, and then it will not change the maximum of that tree. Does that make sense to everyone? Because you're only including values that have a lesser label than the current value you're considering, so it won't affect the maximum value of the tree. So the idea is you can take this 2 by itself, or you can stick the 1 in here. And like if there are more numbers, the way you end up combining it is this kind of expression where you take the product of all the adjacent dpjs plus 1. And what this plus 1, sorry, wait, let's look at chat. Yeah. So the plus 1 is encodes when the adjacency tree is like not used at all. So like you can consider there are dpj plus 1 possible trees that are, there are dpj possible trees that include that value, like dp1 possible trees that include 1. And you can also take the empty tree, which adds 1 to your possible value. Like for example, instead of 2 and 1, you can just take 2 by itself, which doesn't include 1. And that's where that plus 1 comes from. So then you end up just calculating the product of all these dpj plus 1 for all j, such that j is less than I. And you kind of just keep going and activating these numbers from minimum to maximum to calculate the max. You do the same for min, but calculate kind of backwards. And then once that's done, you just do this like sum I times dpi for all I, and you end up solving the actual question. Let me go back to chat really quickly. Could you do this if we weren't guaranteed distinct 1 through n as the labels? I have to think about it, but I think the same approach sort of applies. I think the exact same approach actually applies. Yeah, you just have to sort the labels and continue processing them in sorted order. And the reason this works is like, if you have two labels that aren't distinct, then basically like the first time that you like, yeah, the first time that you process, wait, actually, I think I have to maybe think about that a bit more. I guess it gets kind of nasty when you have like two elements that have the same label that are like located on different ends of the tree. And like, it's hard to have all the information you need to like include that. Yeah, maybe the solution doesn't work fully. I have to think about it a bit more, but possibly a good extension problem to think about. Highly recommend. I don't know if there's a fancy name for the solution. It's just a combination of a few different tricks. I would say like DP in general, DP on trees, and like there's like I think well-known DP that's like the number of subtrees, which this uses. Oh, my solution is not actually in here, but I'll go ahead and share Barrage's, who wrote something pretty similar. Let me just go ahead so you guys can like visualize that. Yeah, so the idea here is like what I said, you just push everything into your like adjacency list. Your base case is like dpi equals 1 because you always have the tree that is just that element by itself. Then you look through all the adjacent elements that are, so like the reason this works, and he's just looking through all the adjacency elements and not checking the ones that are like less than it explicitly, is because all the ones that are greater than it haven't been processed yet, so their value is 0, meaning that they don't affect this product. So yeah, you just iterate through everything in adjacency list and then multiply dpi by I, keep going, and then subtract. So he adds like the first one and subtracts the second one, which ends up giving you the right answer. So let me see, one more question. Yeah, DP on trees is like the general idea. When you're doing DP on trees, this is actually a little different because you're processing in like ordered labels. Typically what you want to do is like process by root, like you want to root the tree at some arbitrary point and like DFS to create a representation and like process with the DFS and come back up. This is like a slightly different way to do things, but I think it's still interesting and good to learn this kind of pattern for sure. Any other questions on any of the problems or just feedback about the contest in general? If we have nothing, I'll go ahead. Congratulations to our winners and our top participants. Well done, Jason Y, Andy Zile, and T-Bobo. That's, yeah. So well done to all three of you. I think Anj/DD can confirm this. I think prizes are, yeah.
Yeah, so we are doing one general prize and one like prize within SummerHacks, but since both of you are SummerHacks, or both of the top two are SummerHacks participants, we're giving prizes to just the two of you. Just like simple. I will message you on Slack or email you if I can't find you on Slack, probably within the next like day or so. If I don't, just message me and just get on me for that. But yeah, I should message you with more info.
Okay, cool. Congrats, everyone. I hope you really enjoyed the contest and you had fun. We'll try to release editorials in the next few days if you didn't pick up anything in this particular session. But in general, I hope you enjoyed, and we'll go ahead and stop the recording and stay behind for any like last questions you guys have.
Thanks for coming, guys. And if you're watching the on YouTube, have a good night.